Hello, welcome back. So today we will look at how to solve systems of linear equalities in two variables. So you might have seen a previous video about solving a single linear equality in two variables. So we're going to build on that and see how to do, we have more than one inequality. So our goals are to be able to solve systems of linear equations in two variables, determine whether or not a solution region is unbounded. We'll explain that, and then also find what I call the corner points of the solution region, which will actually be important in other areas. So a system of linear equalities is basically when you have more than two linear inequalities. So it could look something, for example, this is an example where, like I said in a previous video, we learned how to solve each one independently, but now I want to take a look at both of them together and find the point x and y coordinates that solve or satisfy both these at the same time. So the solution is going to be some region in the xy plane that all the solutions of the individual inequalities have in common. So it's basically points that solve both of these inequalities at the same time, or however many inequalities you have, they have solved them all at the same time. And that's going to be called the solution region, or sometimes called the feasible region. Basically, the set of points, x and y points, that will satisfy all your inequalities at the same time. Now, you also have what are called unbounded or bounded regions. So we say region is bounded if you can draw a circle around it. Okay. If not, it's called unbounded. So basically, imagine some region, we'll see examples of these where you can actually, if you contain to draw a circle around it, that's what's called bounded. But if it goes on forever in some direction, that means you can never draw a circle big enough to contain it, and so that's called unbounded. And finally, a quarter point is the main intersection of the boundary lines of the solution regions. We'll see those, and actually those will be important in the future topics. So let's take a look at our first example. It's going to be similar to this, but not exactly the same. So let's look over here at the right. And so we're actually going to use Desmos to help us out, because basically it's a lot more efficient than trying to do everything by hand. So our first system is going to be 2x plus 5y is less than or equal to 20. And our second inequality is going to be x minus 5y is greater than or equal to negative 5. So I said we're going to use Desmos. Let's look at that. For all of these, we're going to use, once again, it's just go to, just put in desmos.com. So pick up whatever browser you want. So type in desmos.com. Okay. Now, hit graphing calculator. Now, actually, it turns out you can actually only do equations. So if we do the equation, for example, 2x plus 5y is equal to 20, we can do that line. We can also do inequalities. So if I do less than, for example, 20, it actually gives me the solution of that. Also, the dotted line indicating that the line itself is not part of the solution. But I can also do greater than or equal to. So go down to this keyboard down here, click on that. Then you can do the other inequality symbol. So it's equal to 20. There it shows me a solid line indicating the line itself is part of the solution. Now, that's our first one. Now, our other line was x minus 5y is greater than or equal to negative 5. Oops. Okay, so let's take a look. Let's actually move this for a minute. All right, so let's actually also, we can turn these graphs on and off by clicking this. Let's turn this one off for a minute. This is our first one. So here, and both these are, we have the or equal to part, so the lines themselves are part of the solution. So this one, the solution is below the line. Now, look at this one. Solution is also below the line, so the points they have in common are this darker blue region here, okay, that we can see. So let's go back and kind of recreate that. And also these points here, these corner points are going to be useful. This is actually the only corner point we have, 5, 2. Okay, so let's go back and draw that on our really basic graph. Once again, we use Desmos for the more precise graph. So I have this point, 5, 2, which is where the lines intersect. One line looks like this. Okay, this is the first graph. So this is the 2x plus 5y is equal to 20. And then the other line little bit shallower. It looks like this. And once again, you should connect. Looks like more like this. Okay. This is the second line. X minus 5y is equal to 20. Okay. And now negative is equal to -5. Okay. So this is the corner point. So also now this is region. So basically the solutions to this one are below. And the solutions to this inequality are also below the line. So the only region they have in common is this region right here. So this is our solution region. A couple things about it. So it's unbounded. Okay, because let's go back to the Desmos graph. So we can zoom out and we can see there's basically no end to it. Okay, zoom out as much as we want. So the point is I can never draw a circle around any circle I draw, the region will always get bigger than that. So it's unbounded. And actually the only corner point is this one right here, 5, 2. So this region right here with this corner point extending here is our solution region. So you plug in any point within this region. Okay, let's go back, probably better look at the better graph. Plug in any point in this darker blue region where these lines intersect, these regions where both intersect, their solutions to both inequalities at the same time, we'll basically solve both those at the same time simultaneously. For example, like the point 0, 0 is in both. So you see if you plugged in 0 for x and y, you'd have 0 is less than 20, which is true, and 0 is greater than -5, which is true. So any point in this darker blue region is the solution of both at the same time, and that's part of our solution region. Or solution, might be called a solution set, or sometimes called the feasible region. Okay, so that's the solution to our first example. Now, let's take a look at our next example. And this time we're going to have 3 inequalities. So we're going to have 3x, first one, plus 4y is less than or equal to 24. Now we're also going to have x is greater than or equal to 0 and y is greater than or equal to 0, just indicating that both x and y have to be positive or 0. And in many realistic situations, that's going to be true because whatever x is can't be negative, or y is also can't be negative. Let's take a look at this one. So let's go back to Desmos. Okay, get rid of both of these. Let's graph this. So the first one is 3x plus 4y is less than or equal to 24. Okay, so that's that inequality. Then we have x is greater than or equal to 0, and y is greater than or equal to 0. And once we plug these in, we're kind of turn a couple of them off to get a better feel for what we're looking at. Okay, so let's go back and we can click on this to turn them off. So let's look at the first one. And all these have the or equal to part, so the lines themselves are part of the solution, or the solution set, or the solution region. So this one that's below this line. Now, here, this just means that x and y have to be positive. So if you turn both of these on, that's where x is positive, of course, the right half of the xy plane, and y is positive in the upper half of the xy plane. So actually this triangle right here is actually our solution region, okay? And we can actually find those points, those corner points, which are important, okay? So 0, 0, 0, 6, and 8, 0. Let's draw that. Okay, so this line and this line was 3x, let me write over here, a little more space. 3x plus 4y is equal to 24. That's the line. And then the solutions of this one were below it. So I'll just draw little arrows indicating that the solutions to this inequality were the half plane below it. Okay. Then, of course, we had x is greater than or equal to 0. So this is where, of course, well, this is actually where y is 0 on the x-axis. The solutions are above And of course, also x is greater than or equal to 0. And this is, of course, where y is, x is positive. So our solutions are this way. So you can see that our solution region is actually this triangle, okay? And these points, let's go back and double check what they were. 0, 6, 0, 0, and 8, 0. Those are our corner points. So 0, 6, 0, 0, a better 6. And this point over here is 8, 0. Those are our corner points, those three. And then also, this is a bounded region because I could draw a circle around this. It's not going to grow any larger. So I can draw a circle around it. That makes this a bounded, called a bounded solution region. Okay, we have those three corner points. So any point within this triangle, including those corner points, including the lines on the boundary, would be a solution to those three inequalities at the same time. So you can plug in any of those. You can plug in any of those 3 points or any point on the line or any point in the middle, plug those in, and you'll see you get a true statement in each case. Okay. And so then this, once again, this triangle right here, which is the solution of all, the solution of all three inequalities at the same time, is our solution region. It is bounded because I can draw a circle around it, and it's not going to grow any larger. So always be contained by that circle. And so that is a bounded solution region. Okay. Now in future, we talk about in the previous future video, I talked about what's called linear programming, where for maximum minimum values on our solution region, these corner points will become important. Okay, look at the next one, number 3. All right, this time let's do more inequalities in this one. So 3x plus y is greater than or equal to 24. X plus y is greater than or equal to 16. X plus 3y is greater than or equal to 30. And then constraints like I had last time. So x is greater than or equal to 0 and y is greater than or equal to 0. Okay. Now here we have essentially 5 inequalities, but they're all in 2 dimensions, so we can all still use them in the plane. So let's do that. So let's get rid of these. Actually, let's go ahead and get rid of these. Let me turn these off. See if how that will work. Sometimes it gives me weird colors. I have to be careful about that. Make sure they're kind of contrasting. So 3x plus y is greater than or equal to 24. Okay. Double check, make sure that's right. Yeah, greater than or equal to 24. Like they're all greater than or equal to. All right, the second one, x plus y is greater than or equal to 16. And then x plus 3y is greater than or equal to 30. And then our others, so x is greater than 0, y is greater than 0. Now this one, a little harder to see just because of, different colors and everything. So let's kind of take everything apart. Let's kind of unpack it one at a time. Let's start with the top one, this first one. Okay. So, and once again, all these have the or equal to part, so the lines themselves are part of the solutions. So, the solution to this one is on this side. Okay. Now, if I add this one, okay, so now this region here, this intersection of both, is our solution going forward. Let's do the next one. Okay. Now, so here, notice we have this region here, this kind of dark reddish region. Also have a couple of corner points here and here. And then essentially by adding x is greater than or equal to 0 and y is greater than or equal to 0, it just means essentially everything where this is basically in the first quadrant. Okay. So if we do that then, all right, so it's a little harder to see, but let's kind of zoom back in and find out what our values are and our corner points are. And this one is frankly going to be a little bit harder to draw just because we have a lot going on, but that's okay. We'll kind of show our way through it. So in fact, it might be better to draw the solution region itself. So let's zoom out just a bit because what we have is kind of makes like a four. We have 4 corner points, 1, 2, 3, and 4. Let's see if I can draw that. And once again, you can do all this on Desmos on your own. Okay, looks something like this. So we have this, we have another corner point, and going down like that. Now, once again, this is not the best drawing, but you'll get the idea. Now let's go back and look at our corner points. So let's see, we have, this was 4, 12 and 9, 7. Okay, then we also have corner points on this region here as well. So 1 here and 1 here. Let's see what those are. Where that crosses the axis. So 0, 24 and 30, 0. Okay, but it turns out then this then is our solution region. Okay, now I didn't draw the other lines, but basically that's our solution region. Okay, so I have those 4 corner points. Now, if you look at the graph again, we can tell this once again is going to be a case where it's unbounded because we can never draw a circle that's big enough to cover everything. So that's an unbounded region. And there's our corner points here, there, and then this one right here, and then right up here. Okay. Now, so this is unbounded. Solution region. And then we have these 4 corner points for this one. And then once again, what that means, you pick a value on any of those lines or on those corner points or inside this, then that will be a solution. Okay. So get one more example, then we'll do an application problem. Okay, this time, let's do this. So 2x plus 3y is greater than or equal to 24. And then x plus 3y is less than or equal to 15. And then finally, y is greater than or equal to 4. Not 0 this time, but y is greater than or equal to 4. Okay, let's graph these. I'll just get rid of all these to kind of reset our colors as well. So first one, 2x plus 3y is greater than or equal to 24. Okay, that's our first inequality, the solution to that. Then x plus 3y is less than or equal to 15. Okay, then our third one is y is greater than or equal to 4. Okay, so let's take a look. Let's kind of turn them off. So first one is this. Okay, so it's above this line. The next one, okay, include this. So basically, it's these places where the graph overlaps. Okay, so this overlap right here where it's a solution to both. Let's actually zoom in some. And then y is greater than or equal to 4. Now, you notice, also make sure I wrote this down right. Notice actually, this one actually has no solution, okay? Because we're looking for something as a solution to all three at the same time, okay? Once again, so let's turn the y is greater than or equal to 4 off for a moment. All right, so the solution to both of these is this kind of triangular or shape region right here. Of course, this part is unbounded for these two, it goes on forever, okay? Now, once again, we zoom in. Now, if we include this one, so if you want a solution to both these two, it would be this region here, with the corner point right here, where they intersect, 9, 2. But if we include y is greater than or equal to 4, now if we're trying to look at a solution to all three at the same time, there isn't one. Okay, so let me actually kind of draw this a bit, because I want to make sure this is clear. So let's draw this. Okay, so we have our one line down like this, and our second line something like this. And this point here where they intersected was 9, 2. Okay, so this first line was our 2x plus 3y is equal to 24. This line was x plus 3y is equal to 15. And also this, of course, Desmos shows us where they intersect, but if you want to find it by hand where they intersect, you just have to solve both these equations at the same time. But in this case, there's no need to do that since we can use technology to help us out. Okay, now, of course, for both these, the solutions to both of these are below. Drawing these arrows indicate the solutions are below. Okay, wait a minute, I'm sorry, I may have said that wrong, hang on. Actually, I'm sorry, no, our solution is this region here. I apologize. I should have said that. So wait, no, hang on. Sorry, I've had one of the moments. Yeah. So the solutions, the solutions to the top one are above. That's where I was getting wrong. Or it's one of those days. So the solutions of this one are above this. There we go. Okay. I was about to say the wrong thing, which happens sometimes. Okay, so far with just these two, your solutions are this, like I say, this section right here. But now, if I include the third one, which is once again, which is y is greater than or equal to 4, okay, then there is nothing that's a solution to all three at the same time. So that should be a flat line, but you get the idea. So y is equal to 4 above here. Okay, so in this case, there is no solution. I'll say there's no region common to all three uh, inequalities. And so in this case, we simply have no solution, which can happen sometimes. So sometimes you may have, in terms of real life situations, you might have too many constraints or constraints, conditions that conflict with each other. And so you have no solution. That can happen. Just in the same way you can have no solution when you're solving a system of two equations. In this case, we have the situation where we're trying to solve a system of three inequalities, linear inequalities, and they have nothing in common, so there's no solution. No solution or no solutions. Okay, let's look at one more example. This time it's going to be a application problem. Let's read through it. So it says, a furniture manufacturing company makes dining room tables and chairs. The table requires 8 labor hours for assembly and 2 labor hours for finishing. A chair requires 2 labor hours for assembling and 1 labor hour for finishing. The maximum labor hours available per day for assembly and finishing are 400 and 120 respectively. If X tables and Y chairs are produced per day, write a system of linear equalities indicates the appropriate constraints on X and Y. And find the set of solutions or the solution region, the number of tables and chairs to be produced in one day. Okay. Now, it already tells us X and Y, so X is going to be the number of tables, and then Y is the number of chairs. Okay. Now, let's think about what constraints or what inequalities we need. Okay. So you need one inequality. Now, obviously, we're going to need at least two to be able to solve it because we have two variables. One inequality for the, so we have two things happening. So we have assembly and finishing. For one inequality for the assembly. Okay. And so we know the labor hours, the maximum is 400 for assembly. Labor hours have to be less than or equal to 400. Okay. Now, what makes up the labor hours are basically the hours assembled for a chair. So it's basically the hours, let's say hours for tables plus the hours for the chairs. And basically, we're talking labor hours for each is going to be less than or equal to 400. Okay. Now, we'll be able to write then an expression for the labor hours for tables. All right. So look at our information. So we have X tables, and the time it takes to do a table is 8 labor hours. So I want to say 8 hours per chair. So 8 hours per chair times basically X number of chairs. Okay, we can read that, right? It's chairs. Then, so that combines 8 hours per chair times the number of chairs gives us the hours. Well, it doesn't matter. Okay, sorry, I said tables, but yeah, that's either one because I can add in any order. Let's do one for tables then, but the same idea. I have to make sure I use the right, number. So I'm going to do chairs. For chairs, for assembly, okay, for chairs, sorry, that was 2 labor hours per chair. No, I'm doing this backwards. And that's Y was the number of chairs. So it doesn't matter what order I do. So it was 2 assembly hours per chair times Y chairs. Then for the tables, it was 8 hours. I'm having trouble writing today. The table times X tables. And that's got to be less than or equal to 400. Okay. Hang on a moment. I need to find out where. Give me a second. I'm actually going to have to put some more space. I need to do that because I needed more space. I was running out of space here. Okay. So we'll just copy that and put that back up here. Okay, good. All right, so let's continue. And so what that's going to give us then is going to be the inequality. I'll just turn this around. So 8x these are the hours, labor hours to assemble a table, all the tables. you can make, plus 2 times y, the same hours for the chair, is going to be less than or equal to 400. Okay, now we need one more inequality. Abbreviate that for finishing. Okay, and that's going to be, once again, they're going to be the labor hours. Have to be less than or equal to 120. Those are the hours available per day, labor hours available per day for finishing. Now, the same way, do basically the same thing. Okay, so it's going to be the, essentially, once again, the hours for tables, finished tables, plus the hours to finish chairs have to be less than or equal to 120. Okay, now instead of writing this step, let's cut to the chase. So for tables, one's going to do tables first this time. For tables, it was going to be 2 hours for finishing. So 2 to 2x then is the number of hours we can have for that. And so it's going to give us 2x tables. And then for chairs, it was 1 hour from finishing. So it's going to be 1y, or just y. And this is going to be less than or equal to 120. Okay. Now, a couple more constraints. I'd say additional constraints. Okay, we're going to be the x is greater than or equal to 0 and y is greater than or equal to 0, because obviously the number of chairs and tables, they can be 0, they can't be negative. They can be 0, they can be positive, they can't be negative. Okay, so our system then of linear inequalities looks like this. So put it all together: 8x plus 2y is less than or equal to 400. And then 2x rather plus y is less than or equal to 120. Then of course we have x is greater than or equal to 0, y is greater than or equal to 0. So once again, let's graph this. Actually, I may need to erase this, so give me a moment. It's kind of a nice feature if I get it to work, where you actually can circle everything and then delete it. What is that? Okay, let's go back. So we're going to do a Desmos then. And let's plug all these in and see what this looks like. Let's get rid of this. Okay, so our first one, 8x plus 2y is less than or equal to 400. I'm going to have to zoom out some. And then 2x plus y is less than or equal to 120. Okay, then of course x is greater than or equal to 0, and y is greater than or equal to 0. Okay, now let's then turn these off, and let's start with this one. Okay, now we need to zoom out some so we actually see the boundary line. Okay, there we are. All right, now, so that's the first one. The second one, okay, so you can see then this kind of darker greenish region is the overlap. So that's the solution to both these at the same time. So as you can see, we're going to have sort of this triangular region here that's actually our solution region. Okay, if I turn the rest of these on, yeah, it's kind of dark, but you get the idea. So let's actually just, in fact, let's kind of take those off. So let's look at our, let's see if I can zoom in a bit. Yeah. So let's find our corner points. So that one, where those two intersect, is 40 and 40. First off, let's start to draw this. Okay, it looks something kind of like this. Not perfectly, you get the idea. This point right here where they intersect is going to be 40, 40. That's a corner point. Okay, now this top line, if I can double check, that top line is our top one. So that's this line right here. Is the line 8x plus 2y is less than or equal to 400. This line is the other one, 2x plus y is less than or equal, well, sorry, the line itself is equal to 400, and over here, then it's going to be equal to 120, okay? And so both these lines are less than, so basically going in this direction. So our solution region is going to be here. Then, of course, we have y is equal to 0 and x is equal to 0. Of course, those are all going up here and also to the right. So it's getting a little kind of messy here, but just get the idea. So basically, this kind of almost triangular shaped region, except this little notch here, is our solution region. So let's think about our corner points. So we have one here at the origin, 0, 0. Let's find the other two. Another one right here, and another one right here. Let's go back to Desmos, find out what those corner points are. Okay, one is 0, 120. And this one, not actually that right here, but this one right here is 50, 0. This one is 0 and 120. And the other one right here is 50, 0. So let me just, okay. So it's going to be that point. So this is the bounded region, a bounded solution region. And we have 4 corner points. And as we'll see in a future video, we'll talk about actually the other kind of what's called linear programming or optimization. You want to find a maximum value on a region like this. Any point in this region, including those boundary lines, are solutions. Okay, but if you want to find the maximum or minimum value that gives you your best solution, then it turns out it's going to be one of these corner values. Okay, so what we learned to do today are basically to solve systems of linear inequalities at the same time. We also learned that they can be either bounded or unbounded, and then the corner points are important for future interests. Thank you. Have a good day.